So now we know how to test hypotheses and compute p-values when we're talking about a probability or a proportion for something. What if we wanted to do inference about mean values? Well, it turns out we can still do hypothesis tests, and it's really not much harder. For an example to start off, let's remember that data about the patients who had undergone plastic surgery and whether or not that made them look younger. We had data for each patient showing how many years, on average, people seem to think it made them look younger. Now we can say, well, does that mean that for patients everywhere, on average, it's going to make them look younger? Or were these patients just a little bit lucky? So to set this up as a hypothesis test, let's remember the data that we had. In this case, we had n equals 60 different observations of people, and for each one, we had the number of years that they seemed to look younger. Now, if we took the average of those 60 different observations and called it x bar, then x bar was equal to about 7.177 years. And the corresponding estimate of standard deviation, S, was equal to about 2.948 years. So if we want to set this up as a hypothesis test, we can say that in the theoretical world, we have the true mean number of years that this plastic surgery makes you look younger, and we'll call that mu, and that's unknown. Then we also have the estimated number of years that it makes you look younger, and that's our x bar, which is 7.177 years. Now we would like to test whether or not mu is more than 0. So we have a null hypothesis that says mu equals 0, and an alternative hypothesis that says mu is more than 0. To turn this into a hypothesis test, we need to recall something that we learned previously, that in the theoretical world, according to H0, if we look at x bar minus mu and divide it all by the square root of s squared over n, then that has a distribution which isn't quite a standard normal, but is a t-distribution with n minus 1 degrees of freedom, or in this case, 59 different degrees of freedom. So how can we use that? Well, in the theoretical world under H0, where mu equals 0, what we've observed as x bar minus mu is just 7.177. So this means that the p-value should be the probability of observing such an extreme value under the null hypothesis. Well, we compute the probability that x bar minus mu is at least as big as 7.177. Well, we can again manipulate both sides by dividing by the square root of s squared over n. And now we've got a quantity which we know its distribution is this t sub 59. And the question is, what's the probability that that is bigger than or equal to, in this case, 18.86? Well, that's something that, again, you can look up in a table or get the computer to compute for you. And it works out to a tiny number, about 1 chance in a 1 followed by 26 different zeros. Unimaginably small. So we can say in this case, of course, we reject the null hypothesis, and we definitely say that this plastic surgery did indeed make people look younger on average. For another example, let's go back to our old friends, the skeletons, once again. Now, remember with the skeletons, we had the age difference between their estimated age and their true age. We had this observation for 400 different skeletons. And in that case, out of these different observations, we computed that x bar, the sample average of the difference between the estimated minus the actual age, was equal to 14.15 years. And the corresponding estimate of standard deviation, S, was equal to 14.13 years. It's just a coincidence that those two numbers are so similar. That doesn't mean anything. In this case, we're just trying to figure out whether this mean is something that's different from 0. So it means we want to use a two-sided test. And our null hypothesis should be, in this case, that mu is equal to 0. That is that on average, there's no difference between the estimated age and the actual age for these skeletons. Our alternative hypothesis is just that mu is some number which is different from 0. Again, we don't want to specify now whether it's bigger than 0 or less than 0. We're just testing whether or not mu is equal to 0 or equal to some other value. Now, in the theoretical world, we know that x bar minus mu divided by the square root of s squared over n has approximately a t-distribution with n minus 1 degrees of freedom, in this case, n is 400, so n minus 1 is 399. So that means that if we want to compute a p-value, then we want to compute the probability under the null hypothesis of observing, in absolute value now, because it's a two-sided test, a value which is that extreme or more extreme for the difference between mu and x bar. Well, we can compute the probability that x bar minus mu in absolute value is bigger than or equal to the observed value, which is the absolute value of minus 14.15. Well, we can use our old trick. We divide both sides by the square root of s squared over n, and we eventually say it's the same as the probability that the absolute value of the t sub 399 distribution is bigger than or equal to 20.03. Now, one trick is the probability that an absolute value of something like a t distribution is bigger than or equal to some value is just twice the probability that the value is less than or equal to the negative of it. Because again, the absolute value can be bigger if either the value is bigger or the value is smaller than the minus of it. So it's 2 times the probability that a t distribution with 399 degrees of freedom will be at least as small as minus 20.03. And you can work that out. It again works out to be an unimaginably small number. In this case, something like 1 over 3 followed by 61 zeros, just unimaginably small. So in this case, we can say again that we reject the null hypothesis and we say, no, it's not true that those skeletons stay the same on average. In fact, those skeletons, on average, the estimated age is, well, in this case, actually smaller than the true age. But in any case, we can say that the estimated age minus the true age is not equal to 0 on average. So let's do one more example. In this one, let's remember Allison's data about people's true body temperature. And remember, there's a long-held belief that, well, the average true human normal body temperature is equal to 37 degrees Celsius or 98.6 degrees Fahrenheit. But some people have wondered whether that's true. And remember, they did an experiment where they got 130 different people and they measured the temperature of each one. And they got different values like 36.67 and 37.22 and so on. And these were different values of the temperature of these different subjects. And then they said, well, does this confirm or deny the possibility that the true average human body temperature is equal to 37 degrees? Well, to set this up as an experiment, we can say that the null hypothesis now is that the true normal human body temperature, mu, is equal to 37 degrees. And the alternative hypothesis is that it's something else besides 37 degrees. Now, in this case, we don't have any prior knowledge of whether it's more or less. So again, we'll do a two-sided test. So in the theoretical world, again, assuming the null hypothesis, we can say that, well, x bar minus mu over the square root of s squared over n should have a t distribution with n minus 1 degrees of freedom, or 129 degrees of freedom. So what does that mean? It means that the p-value should be computed by saying, what's the probability that the actual difference in absolute value of x bar minus mu is at least as big as the observed difference, which in this case was 36.80513 minus 37, which is about minus 0.19487. It's a rather small difference, but what's the probability we would observe at least that large a difference, assuming h0? Well, again, we know how to work this out. We start by dividing both sides by the square root of s squared over n and rearrange, so we eventually get it to be the same as the probability that the absolute value of something with a t distribution with 129 different degrees of freedom is bigger than or equal to, well, in this case, it works out to 5.455. And again, that should be twice as much as the probability that the t distribution is less than or equal to minus 5.455. And again, this is something we can look up in a table or get the computer to compute for us. And we find out again, it's extremely small. It's about 1 chance in 4 million. So once again, we can reject the null hypothesis and say, no, it's just not true that the average normal human body temperature is equal to 37 degrees Celsius. It seems like it's close, but it's a little bit less than 37 degrees. So in this way, we can do hypothesis tests and compute p-values even when we're talking about a mean or an average value. And once again, we can decide when to reject the null hypothesis and when to accept the null hypothesis, and we can decide whether or not the mean values are bigger than or smaller than or equal to certain values.